Hey guys, this is AS Organic Isomerism. There are two isomers that you need to know of in AS Organic: structural isomerism and stereoisomerism. In this video, we'll do structural isomerism. So, what are isomers? Isomers are compounds that have the same molecular formula but different structures. Suppose that I have this molecular formula C4H10 and I'm asked to draw the structure of C4H10. So I'd start with 4 carbon atoms, the longest unbroken carbon chain, and 10 hydrogens, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens. What do I name this? I would name this butane. Now, what if I told you that I can draw C4H10 in a different way? Suppose I take this carbon right here, the terminal carbon. By the way, these two carbons are known as the terminal carbons because they are at the end of the carbon chain. So what if I take this terminal carbon and say move it to this carbon right here? Replace this hydrogen with this methyl group, right? Let's do that. So 1, 2, 3, 1, 2, 3, and I take this carbon, right, which was originally right here, and I move it to this central carbon. So simply I took this, moved it right here. Now I would draw the hydrogens like I would draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hey, guess what? These are still 10 hydrogens. This is C4H10, right? And surprisingly, this is also C4H10 because 4 carbons and 10 hydrogens. So when a compound has the same molecular formula, but different overall structure, right? Different structure, then it is said to be an isomer. These two are isomers of each other. What would you name this? This has the central carbon chain. The longest central carbon chain is of 3 carbon atoms, so this is propane, and the methyl group is on carbon number 1, 2. So this is on carbon number 2. The methyl group on carbon number 2 would mean 2-methyl, right? So 2-methyl propane, and this is butane, but both of them are C4H10. So for two compounds to be an isomer, 1, they must have the same molecular formula. 2, they must have different structures, right? And 3, they must have different names, right? Now, what if I told you that I take this carbon atom and I replace it here instead of moving it here? What if I put it on this carbon atom? Well, let's do that. So 1, 2, 3, and then this terminal carbon would come right here, right? And 10 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So is this an isomer or no? It's not an isomer. Why is that? Well, because you cannot manipulate the carbon chain and add the methyl group on the terminal carbons. So this would still be read as butane because the longest, this is still an unbroken carbon chain, right? So this does not have any branches. I can read it like this. So meth, eth, prop, bute, ane. So this has the same name. That means if a compound has similar names, they are not isomers. So these two are not isomers of each other. Now, there are 3 different ways you can make structural isomers: by manipulating the chain of the main structure, or the position of the functional group, or the functional group itself. Let's start with what is meant by chain. So manipulating the chain means you manipulate the carbon chain. The example I showed you earlier where I drew butane and 2-methyl propane, you tell me, was this an example of chain isomerism? Yes, it was. Because what is chain isomerism? I told you earlier, chain isomerism is manipulating the carbon chain. And hey, look, I took this carbon from the main carbon chain and I placed it right here. So I manipulated the carbon chain because this right here was the biggest unbroken carbon chain. So I took this carbon chain, moved it right here, and I formed 2-methyl propane. Now, this is an example of chain isomerism. Let's do another example of chain isomer. Let's say I have a molecular formula of C5H12, and in the exam I'm asked to draw the different isomers. First of all, I would always start off with the simplest carbon structure that I can make, which is the longest unbroken carbon chain of 5 carbon atoms and 12 hydrogens, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 hydrogens. And this is pentane. Now, can I draw this? Can I manipulate the carbon chain so that it gives me a different name than pentane? I can take this carbon atom and place it right here on this carbon atom right here. Like I took this carbon atom and I would place it right here. That would give me this structure. And what would be the name of this? Meth eth prop but, so butane. And the methyl group is on carbon number 2, so 2-methyl butane. And you can see that this will still have 12 hydrogens, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 3 hydrogens here would be 10, 11, and 12. So C5H12 still, and C5H12 here as well. C5H12, C5H12. So these two are said to be isomers. Now, is there another way I can draw this structure of C5H12 so it gives me a different compound with a different name? What if I take this, right? What if I do this? 3 carbon atoms, and I would place 2 carbon atoms on carbon number 2. This is, remember, it must be C5H12. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 hydrogens again. And what would be the name of this compound? If this compound has a different name than pentane and 2-methylbutane, then it would be an isomer. So the longest unbroken carbon chain again is 3 carbon atoms. So meth eth prop. This is again prop. But now it has 2 methyl groups, right? So I would call it dimethyl. So, and remember that the methyl groups, both of these methyl groups are on carbon number 2. So I would say 2,2-dimethyl. 2,2-dimethyl propane. This was one structure, this was another structure, and this was another structure. So, and all of these have different names and different structures, and they have the same molecular formula. So all 3 of these are chain isomers of each other. Now, what if I told you C5H12 has a different way of being drawn? Let's say I take 1, 2, 3, 4, and say 5. What did I change here, right? So in pentane, I took these 2 terminal carbon atoms and moved it to these adjacent carbon atoms. So I got this structure right here. Is this an isomer or no? It's not an isomer. Why? Because this is still the longest unbroken carbon chain. Because remember, these 2 carbon atoms, these 2 right here, are not branched methyl groups. These are simply part of the carbon chain because this is unbroken. The next structural isomerism you need to know is positional isomers. In positional isomer, you are changing the functional position of the functional group so that it gives you a different name. You're not changing the carbon chain, you're only changing the functional group position. What do I mean by functional group position? Well, let's say I have 4 carbon atoms, right? And I have a double bond, say, right here. This would be butane, right? Butene. I can write but1ene or simply butene, doesn't matter. But this is butene. Point is, this is butene. What if I take this double bond and place it right here? I shifted the position of the double bond to the next carbon atom. What would be the new name for this compound? It would be, again, it would be butene, but now since the double bond is on carbon number 2, then this would be but2ene. And how many hydrogens do I have? I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, C4H8. This is C4H8. And how many hydrogens and carbon atoms does but1ene have? Well, for that I would take this carbon chain, place it right here again, and now simply removing this double bond. So 1, 2, 3, 4, 5, 6, 7, 8. This is also surprisingly C4H8. So both of these have the same molecular formula, therefore they are isomers of each other. More specifically, they are positional isomers of each other. Let's say I have C3H8O and I have been told to draw the positional isomers of this molecular formula. First of all, what kind of functional group would C3H8O contain? I know it has an O, so it must have an aldehyde. It can be an aldehyde, it doesn't have to be an aldehyde. It can also contain an alcohol, right? Because alcohol is OH, so one oxygen would mean alcohol. Aldehydes is double bond O and CH, so again one oxygen. It can also be an aldehyde, and it can also be a ketone, because ketone is C double bond O with carbons on adjacent sides. It cannot be a carboxylic acid because carboxylic acids have C double bond OOH group, and nor can it be an ester. So let's do all of these possibilities. Let's start with aldehyde. Again, biggest unbroken carbon chain of 3 carbon atoms. So, and 8 hydrogens. So 1, 2, 3, 4, 5, 6, 7. So double bond O. And this is giving me C3H7O. With three carbons, I can only have a maximum of 7 hydrogens. So it cannot be an aldehyde because I have 7. And let's do an alcohol now. Again, 3 carbon atoms, biggest unbroken carbon chain, and 8 hydrogens, right? So 1, 2, 3, 4, 5, 6, 7, and then I must also have an O, so the alcohol, let's say it comes here. So 1, 2, 3, 4, 5, 6, 7, and 8 hydrogens and 1 oxygen. So yes, congrats, this is giving me C3H8O. So that means this is an alcohol. But can it be a ketone? Let's do a ketone as well. 1, 2, 3 carbon chain, 1, 2, 3, 4, 5, 6, and then double bond here. This is C3, 1, 2, 3, 4, 5, 6, H6O. So a ketone does not give me C3H8O. Therefore, the only possible structure of C3H8O would be this right here. Now that I have drawn the structure, what would be the positional isomer of this? Well, simply I would take this OH and move it right here. Remove this OH, place it right here, and then I would have 1, 2, 3, 4, 5, 6, 7, and 8 hydrogens and still oxygen. And since I moved the position, this would have a different name. So originally I had the OH placed on carbon number 1, but then I moved the OH on carbon number 2. And both ways I get the same molecular formula, but since I changed the position, I would now have different names. Again, this would be prop. This would be prop as well because 3 carbon atoms. But the alcohol is on carbon number 1 here, and in this structure right here, it's on carbon number 2. So prop 2 all, and this would be prop 1 all, or propanol. My bad, prop, and there should be an an. The point is that this has propan 2 all as the name, and this has prop 1 all as the name. And since they have different names but the same molecular formula, they are positional isomers of each other. On to the last one, functional group isomerism, which is when you manipulate the functional group itself to create two different functional groups. Well, let's say I have C2H4 and O2, right? And what are the different functional groups that can be formed in this molecular formula? Just the possibilities. I can have two alcohols. Can I have two alcohols? Yeah, because I think we can, but we'll see. Two alcohols, and then I can have, let's say, I can have two ketones. Can I have two ketones? No, I cannot have two ketones because there is no carbon right here. What I can have is an aldehyde. Can I have an aldehyde? Let's see. Well, for an aldehyde, I must have C double bond O and H. This would be an aldehyde. But how many hydrogens do I have? I have two hydrogens, right? But I need four hydrogens. That would mean I cannot have an aldehyde as well. So can I have two alcohols? Let's see. I have two carbon atoms, right? Two carbon atoms, and let's place the OHs on adjacent carbon atoms, and then hydrogen, 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 and hydrogen to fill up the space. So 1, 2, 3, 4, 5, 6. Oh, I cannot have two alcohols as well because, my bad, because molecular formula says 4. I have 6 hydrogens. So now, what else can I have? I can have, let's see, can I have an acid, carboxylic acid? Can I have an ester or a carboxylic acid? Let's see. Well, two carbon atoms, and then double bond O, and then an OH. That is one carboxylic acid group, and I would then place hydrogens on this carbon atom, right? So yeah, 1, 2, 3, 4. Whoa, it gives me 4 hydrogens and two oxygens, and two carbon atoms. Congrats, we have C2H4 O2. So I can have a carboxylic acid, right? Now, for this molecular formula to be showing functional group isomerism, I must have another structural formula which has a different functional group than an acid. I must have a different functional group which must not be a carboxylic acid. So what can it be? I know it can be, let's see if I know it can't be an alcohol nor a ketone or aldehyde. So the only option I am left with is an ester. So let's see if I can draw an ester. For an ester, I would have C, right, which has a C double bond O and then an O. This is an ester group, right? And then let's say I place this carbon right here. So I have two carbons completed. Now the only thing left is to place the hydrogens. So if it gives me 4 hydrogens, that means it must be functional group isomers. These two are functional group isomers. So let's see, 1, 2, 3 hydrogens right here, and then I can place 1 hydrogen right here, right? And this would give me C4H8O2, and this also gives me C4H8O2. Both have the same molecular formula and both have different functional groups. Both contain two different functional groups. This carbon right here, carbon compound A, contains a functional group called carboxylic acid. This compound B has an ester. Both of these are different functional groups, so yes, it is a functional group isomer. Let's say I have these three compounds, and let's count them and make the molecular formula. All of them contains 4 carbon atoms, so C4. This one has 3, 4, 5, 6, 7, 8 hydrogens. This has 3, 3, 6, 7, 8. So this has 8 hydrogens as well. This one also has C4 and 3, 4, 5, 6, 7, 8. So 8 hydrogens as well. And remember, all of these are same molecular formulas. So all of these three may be isomers of each other. There are two conditions for them to be isomers of each other. Must be one, they must have same molecular formula, and the second thing is different names. So if I know that all of these three compounds have same molecular formula, and if they also have different names, then all of these three are isomers of each other. Let's name this. This is easy, butene. This would be propene, right? But since it has a methyl group, this would be 2-methyl propene. Butene. So since all of these have different names, right? And they have the same molecular formulas, they are all isomers of each other.